Welcome back to my course. There is the aspects of biochemical engineering. Now, in the last lecture, I tried to concentrate on the thermodynamics, and with thermodynamics as a whole, how thermodynamics, what is the definition of thermodynamics, and then also we also discussed the spontaneous reaction, non-spontaneous reaction with respect to the change of entropy, with respect to the free energy change, and we have given how to calculate the entropy of the process, that we can easily do that. Now, this particular lecture will give you more stress on the chemical thermodynamics. Now, first thing that I want to show you, that is the thermodynamics of biomethanation process. As you know that biomethanation process is kind of anaerobic digestion process, where the organic material is converted to methane and carbon dioxide. Now, when it produces methane and carbon dioxide, this usually takes place in two different stages. One is called acid formation, another we call gas generation. Now, in case of acid formation, mostly it produces the volatile fatty acid like acetic acid, propionic acid, butyric acid, and this acid subsequently that will be converted to methane and carbon dioxide. Now, this here we have given some examples that the kind of free energy change that we have in this so, when you consider the glucose in presence of water, it produces the acetic acid and hydrogen like this, and this is the carbonic acid, and the free energy change is minus 49.2 kilocals. Now, this again this carbonic acid in presence of hydrogen, it produces acetic acid. The 1 mole of glucose usually produces 3 moles of acetic acid. Now, we have total free energy change of this system is 74.3 kilocals. So, this free energy change clearly indicate that the reaction is favorable. Now, if you look at the anaerobic digestion process, when you carry out the anaerobic fermentation process, the acid formation process are quite fast, and so we do not have much of problem with the acid formation process. Now, let us this acid also can be formed from the carbon dioxide. You see, the carbon dioxide and hydrogen that form acetic acid, but if you look at the free energy change is minus 18.7 kilocals. Now, this free energy change and what we have previously free energy change, this is much less as compared to that. So, that indicates the previous reaction is more favorable as compared to this reaction. Now, when this carbon dioxide and hydrogen forms the methane and water, the free energy change is minus 33.2 kilocals. That means, when this carbon dioxide and hydrogen is most favorable for the production of methane rather than for the production of acetic acid. Now, here as I pointed out that intermediate, the volatile fatty acid that forms in this reaction is the acetic acid, this is propionic acid, and this is the butyric acid. Now, when this acid is converted to acetic acid, this is converted to methane, and this so you find that if you look at the free energy change, this conversion propionic acid to acetic acid is not favorable. The free energy change is plus 19.5 kilocals, but butyric acid to acetic acid is 9.95 kilocals. Now, those who has the experiences with the anaerobic digestion process, they know when we operate the anaerobic digestion process for longer period of time, we find the accumulation of propionic acid that take place in the system, because the reason is that you can find out is that thermodynamically this degradation is unfavorable. That is why we get in the long time operation, we get in the fermentation broth, we get more accumulation of propionic acid rather than butyric acid or acetic acid. Now, another is that the how NAD pH that converted to hydrogen and then to this hydrogen how is converted to methane. So, overall that conversion process is like this minus 14.8 kilocals. So, if you now if you compare this with the previous result, you will find previous reaction by if you look at this one and if you look at this one, you will find this reaction is favorable as compared to this reaction. This is how we can thermodynamically how we can determine which reaction is favorable, which reaction is unfavorable. Now, heat of formation, that the enthalpy of formation, that how is the enthalpy change when 1 mole of pure compound is formed from its element. Most stable state is called the enthalpy of formation, is denoted as del HF. Now, graphite when you heat with water, heat with oxygen, it produces in presence of oxygen. When graphite burn, it produces carbon dioxide, and this is carbon dioxide is quite stable form, and the heat of formation is minus 393.5 kilojoules per mole. Now, the enthalpy of combustion, now that is the enthalpy of formation. I shall solve one problem, then there the enthalpy of formation will be much clear. Now, here the enthalpy of combustion means you burnt ethanol in presence of oxygen, and what is the final product that we have? Final product we have carbon dioxide and water, and this is heat of combustion is minus 1365.5 kilojoules per mole. The enthalpy of combustion, so we can express as this. Now, there is a important law, what is called Hess law. The Hess law says that the standard enthalpy of a reaction is the sum of standard enthalpies of the reaction in which the overall reaction may be divided. So, this I shall show you that how this analysis can be done. So, let me tell you again, the Hess law says the standard enthalpy of a reaction is the sum of the standard enthalpy of the reaction in which the overall reaction may be divided. If I solve one problem, I hope the conception will be clear. Let us take the example of the biological system. This is in a biological cell that have a plenty supply of oxygen, a plentiful supply of oxygen. The glucose is oxidized completely to carbon dioxide and water. Muscle cells may be deprived oxygen due to the vigorous exercise, and in that case 1 mole of glucose is converted to 2 moles of lactic acid by the process of glycolysis. Given the thermodynamic equation of the combustion of glucose and lactic acid is given here. This is the so here I can see this is glucose in presence of oxygen. It produces carbon dioxide and water, and change of enthalpy is 2808 kilojoules. Now, when lactic acid, this is the lactic acid, when it burns, it in presence of oxygen, it also produces carbon dioxide and water. Change of enthalpy is 1344 kilojoules. Now, that we calculate the what we shall have to do, we shall have to calculate the standard free energy change standard enthalpy for glycolysis from glucose to lactic acid, 2 moles of is the biological process advantageous to complete oxidation of glucose compared to glycolysis? Expand your answer. So, which one is more advantageous in the biological system energy point of view, whether glucose should be converted to carbon dioxide and water, or glucose should be partially converted to lactic acid. So, this problem deals with that. Now, previously we have seen this is the equation that we have. Now, here here what do we have? We have seen that that 1 mole of this glucose produce 6 moles of carbon dioxide and 6 moles of water. It has this. Now, 6 moles of carbon dioxide and 6 moles of water, it can produce 2 moles of lactic acid and 6 moles of oxygen, and that required the enthalpy 2 into plus, because it was minus previously. Since it is reverse direction, it will be plus. The rate of formation, previously it was the rate of degradation. So, it is plus 134 points. So, if you see the overall reaction, if you minus this, then this will be cancelled. Then I can write that 1 mole of glucose produce 2 mole of lactic acid, and if you deduct from this, your that enthalpy change is coming around 120 kilojoules per mole. So, what does it indicate? It indicates that it follows the standard enthalpy for the conversion of glucose to lactic acid during glycolysis is 120 kilojoules per mole, is merely the 4% of the enthalpy of conversion of glucose, because amount of heat enthalpy generated during conversion of complete conversion of glucose to carbon dioxide water, it will be 4% of that, and therefore, full oxidation of glucose in metabolic is more useful than glycolysis, because the former is more energy process, more energy become available for the performing the work. So, if you energy point of view, that glucose to carbon dioxide and water is more attractive as compared to glucose to lactic acid. Now, I have taken another example, that is the heat of formation of ammonia, and the heat of combustion of ammonia and hydrogen is given here. You can look at here. This is the heat of this is the how ammonia is the heat of combustion. How we can calculate heat of combustion of hydrogen? We can we can calculate like this, and 3 moles of hydrogen combustion, we take 3 into this. So, as per this reaction, we can calculate this one. Now, if you look at the for 2 moles of ammonia, we required 1 moles of nitrogen and 3 moles of hydrogen. The reversible. So, if this formation, what we required? We required if you subtract 3 from 1. So, we subtract this to this. Then we will find this equation. This is 2 moles of ammonia and degraded nitrogen plus 3 moles of hydrogen. So, if you calculate from here, you will find this is the plus 188.58 kilocals. Now, this is the ammonia degradation, but we want to calculate the heat of formation of ammonia. So, it will be reversible reaction, the reverse reaction other direction. So, it will be negative. This is positive in case of degradation, but in formation it will be negative. So, heat of formation for per 2 moles of ammonia is 188.58 kilocals. So, per mole of ammonia will be divided by 2, that is 94.29 kilocals. Now, so we in the last lecture we discussed about the equilibrium of the kind of process that we have. Now, another very interesting thing is that equilibrium that is largely applicable in the chemical process. Chemical process, particularly if you look at the biochemical reaction, if we look at our metabolic pathway, most of the reaction they are reversible in nature. And when we carried out any kind of reversible reaction, like A to A reversibly give A to B. So, there is a forward reaction, this is forward reaction and this is the backward reaction that we have. So, under equilibrium condition, the rate of forward reaction should be equal to rate of backward reaction. So, that is the under equilibrium condition. So, that from that we can find out the equilibrium constant. The state of reversible reaction in which the concentration of the reactant and product do not change with time is called the chemical equilibrium. When that is exactly, I told you that when rate of forward reaction is equal to the rate of chemical reaction, then we call it is equilibrium conditions. Now, the characteristics of chemical equilibrium are several. The reversible reaction attains a state of equilibrium from reactant and product side, and at equilibrium the reactant and products both present and their concentration do not change with this. So, if you look at the rate of suppose A to B, B to like this. So, this is the rate of this is the rate constant for the forward reaction is K and this is K minus 1. So, I can write what is the rate of forward reaction, it is K1 into Ca, and this should be equal to K minus 1 into Cb. So, this is at equilibrium condition it will so if you consider the equilibrium constant capital K, this should be equal to Cb by Ca, or I can write this is K1 by K minus 1. So, this is how you can calculate the equilibrium constant. The equilibrium is the dynamic in nature and reaction does not stop at this stage, but take place in both the direction with equal speed. Now, this is the equal speed it takes place. The equilibrium state is not affecting the presence of catalyst. This is very important. It only helps to attain the equilibrium state rapidly. The purpose of the catalyst in a reversible reaction is not change the equilibrium constant, but it will help to attain the equilibrium constant at a faster rate. The state of equilibrium disturbed when the pressure, temperature and concentration of reactant and products are changed according to the this is according to the Lee-Catlier principles. The free energy change is 0 is at equilibrium. This I already explained in the last lecture. Now, we can explain the reaction like this. A, P, with so rate of forward reaction is explained like the rate of because the backward reaction is so under equilibrium condition both are same. So, equilibrium constant is basically this is equal to concentration of product divided by concentration of reactant. The equilibrium constant of a particular reaction is concentration of product by concentration of reactant. Now, one important thing is what are the factors who do not influence the equilibrium constant. First is the concentration of reactant of product, because that I can explain you K equal to concentration of substrate and concentration of product. Now, what do you mean that concentration? Suppose the concentration of product is changes, the concentration substrate will be changed. So, that change in a manner so that we can attain the equilibrium condition. So, okay, this I write wrongly, this will be product, sorry, this is product by substrate, sorry, I do write it wrongly. So, as the product concentration increases, the substrate concentration should be increased, so that K it remain constant. Now, one interesting feature is that suppose if we want to increase the product formation, what is our goal? Our goal is to get more product. If we want to get more product, if we take out the product time to time, and then more substrate will be converted to product to keep the equilibrium constant. Now, the examples are that the ethanol fermentation process. Ethanol is a volatile component. At the vacuum, at a low temperature, we can volatilizes the ethanol. Now, if you take out the ethanol, more substrate will be converted to ethanol, our productivity of the system will be increased. The pressure and volume does not affect this. So concentration doesn't affect money. As this changes, this also changes. Then ultimately they will be constant. The concentration do not affect the equilibrium much, because and pressure and volume, that also doesn't affect the equilibrium. Presence of catalyst, that also does not equilibrium, and introduction of inert gas, that also will not affect the equilibrium. Now we have, if you look at the for endothermic reaction, that K equilibrium increases with the rise of temperature and decrease with the decrease of temperature. But in case of exothermic reaction, it will be reverse. That the equilibrium constant will decreases with rise of temperature and increases with decrease of temperature. Now, if you burned up, they explain the effect of temperature on this equilibrium constant by this equation log the equilibrium constant of EQ2 and EQ1 at two different temperatures. It can be explained. This is a change of enthalpy. This R is the gas constant, and this can be that explained like this. Now, how we can correlate this with the Gibbs free energy change for the reversible reactions. So, we have already find that change of free energy we can explain like this: the change of the free energy of the product minus free energy of substrate, that is give the change of free energy, and this is G A is the A of and G A minus G A dash. This is the standard free energy change. It can be explained by RT ln concentration of A, GB by GB 0 power 0 ln, and this change of entropy can be change of that free energy change can be written as that standard free energy change plus RT ln concentration of product by concentration of substrate. This can be explained like this, and this is very important. Why it is very important? Because this is del G equal to del G0 plus RT ln K equilibrium constant. Am I right? Now, since the equilibrium constant is constant for a chemical reaction, reversible reaction, so we can del G value also constant. So, if it constant, so we del H value, if we have a chemical reaction, we can find out easily, we can calculate the value of Ke value, and we can find out at what extent the reaction takes place. So, this is one of the major purpose of the thermodynamics of the chemical reaction, that tells you that to what extent the reaction takes place. Now, here del G equal to RT ln this if you solve it here, and if we at equilibrium, if you find out that if you assume that the equilibrium the change of free energy change is 0, then standard free energy change equal to minus RT ln K. So, if we know in a particular chemical reaction, if we know the standard free energy change, from that we can easily calculate the equilibrium constant. Now, here the very interesting thing is that if K, if we have K equilibrium constant greater than 1, then the log K ln is positive, del G equal to negative. And if this is less than 1, then log K is negative and del G will be positive. So, if del G is this equal to standard free energy change is 0, then K equivalent is 1, but if del G is less than 0, then K is greater than 1, and when del G is greater than 0, that is positive, then K is less than 1. So, this is the this is how there is a correlation between the Gibbs free energy change and the equilibrium constant, it can be explained like this. Now, this is a problem that we have, but this gives you some idea that how we can find out that equilibrium constant of a reaction with the help of free energy change. The problem says that at 200 Kelvin a certain reaction that del G is 5.08 kilojoules per mole. What is the K equivalent equilibrium for this reaction at this temperature? And I told you previously that this gives free energy change, that correlation also help you to find out the equilibrium constant. Now, we have the correlation of the free energy change, standard free energy change equal to minus RT ln Ku. Now, Ku, K equilibrium constant, that this is not given. We have the rate constant 8.314, this is known to us, and temperature is 2000 Kelvin, and your change of free energy is this. Then we can find out that that means if K is fraction, that means your del G, as del G is less than 0, is greater than 0, then K is less than 1. So, this is justified, because if you look at sorry, we have seen here, if K is less than 1, then this should be positive, more than 0, that is only positive. So, in this problem, it is clear that this is less than 1. So, K is less than 1. So, this should be positive. So, this is quite relevance to this what we told you previously. So, in conclusion, I want to point out that what we get from the reaction thermodynamics. Reaction thermodynamics basically gives us couple of information. First information we get that how the entropy influence the nature of the reaction. I told you if entropy is positive, then the reaction will be spontaneous, and when entropy is negative, that is not spontaneous. And same thing happens to we can correlate the free energy, Gibbs free energy change, how the standard free energy is correlated to the nature of reaction. If the Gibbs free energy change is negative, that means it is a exothermic reaction. If it is positive, it indicates the endothermic reaction. Now, the Gibbs free energy change is equal to minus RT ln equilibrium constant. Since the equilibrium constant of a particular chemical reaction is constant, so we can with the del G value, that at a particular temperature that should be constant. From that we can find out that to what extent the reaction take place. Suppose if we know the free energy, standard free energy change of a chemical reaction or biochemical reaction, we can easily find out that equilibrium constant. We try to solve one problem, and you find out that how the equilibrium constant can be determined from the standard free energy change. So, so basically that thermodynamics gives two different informations to us, that what is the nature of the reaction that take place. Second information that we have to what extent the reaction take place. Thank you very much.